Welcome to the second video. In this video we will be covering sections 3 and 4. Okay, section 3 is about a circular linked list. We've done a few of these, at least turning them in with linked list. I don't think we ever did a circular linked list, but this needs to be a circular linked list that is doubly linked. And for each step, I've drawn the final step on each one. What you should do in your thing is kind of draw what's done first, second, third, fourth with the different links and everything like that. Sometimes it doesn't matter what order it's done, but some other times it does. So if we have a circular linked list and we just start it and create and add able to it, what we do is we create we have our head and tail. The first thing we probably do is create the new node able and assign the data to that. When we add able, it's onto a blank list, so head and tail is pointing to null, so we draw those and connect those to the new node that we created, able. Since able is being added to the list as itself, what I've done also to kind of make everything a little bit easier is all next lines for the node are exiting the right hand side of that square, and all previous nodes exits from the left hand side. Sorry about the arrows, but I kind of just had to trace this on my computer to get it done. So what we see is the next node of able points back to itself because it's a circular linked list, so there should be no nulls in this list. And the previous node of able also points back to itself. So every time we call next, we essentially look at the reference and it points back to itself. So that's adding able to the list. So then we take that list and add our next item onto it, which is Baron. Here we create our new node Baron, and based upon that, what we would do is, since we're adding it at the head, we would take the Barons next and point that to the current head, which is able. Then what we could do is take able's next and point that and have that now point to Baron, because able is now the tail of the list, and so whoever's the tail of the list should point back to the head. Baron's previous should point to, since it's the head, should point to the tail, and that is able. And then able's previous, since it was previously itself, should now point out to Baron. So just when you add these guys, make sure you order them in the way that they should be added into the picture here. I believe the first thing should be changing or leaving the head, creating the node Baron. Since able was the previous head and now Baron is, able's previous should now point to Baron because that's the new head. And since able's next was pointing back to itself, and it is now the tail, it should point back to the head, which is now should be now pointing to Baron, and then Baron just should be pointing out to able at the correct previous and next locations. Okay, so that's adding Baron to the head of the list. Then what we want to do is add Charles to the tail. So we create our new node Charles. The old tail was able. So when we're adding it to the end, the new tail, the previous tail able now points next to Charles. Charles previous would point back to able. Then we got a new tail node, and because we got a new tail node, the previous head now would get reassigned. The previous of the head node would get assigned to the new tail, and Charles, since it's the tail next, should now point out to Baron as the new node. So those are then the changes of adding Charles at the tail. We remove able in the middle. So we find able, then we remove it. So we look at able's next previous, which is Charles, which should point back to able, and we take that Charles previous and point that back to Baron. Baron's next, which was pointing to able, should now be Baron's next, which now should point to Charles, which it does. Charles, I believe that's it. Those are the only two nodes pointing back to it. So now that we remove able and remove the references, we probably should set able's next and able's previous to null, so that garbage collector can then clean up able's node. So that is the final picture of able there. We would probably draw Charles over here and then draw the nodes being deleted at the correct time, or the lines, the references. Here we add Devon. This is very similar to when we added Baron at head. Just a new node here. So we add the Devon at the head of the list, and there's our resulting circular linked list of adding Devon at the head of the circular linked list. And then we decided that Devon shouldn't be there, and we removed Devon altogether. So we revert that back to what it previously was with this picture. So section 4 is the reallocation method. Previously I described it in terms of initial capacity. Obviously I explained it a little bit differently now. However, what we should do is still go through and kind of draw out the picture that we showed. For you guys that remember in class when we described it, we drew a picture of of an array of 4 slots. Filling up that array of 4 slots costs 4. When we add the 5th element of that, what we have to do is create another array of double that size, copy all the elements from the old array to the new array, and then add the new element. So to go from 4, which to fill up that array is O to the 1, because it just simply every add happens at the end and it's only O to the 1. Now to add the second array and to fill up that with our 5th element, worst case scenario is right after the doubling of it, so it cost us 9 to move it. The 4 to initially add the 4 elements, 4 more to copy the 4 from the full array to the expanded array, plus 1 more to add it to the end. So that's 4 plus 1, which gives us 9 to insert, and we've inserted 5 elements. So you can think of that as 9 over 5, which gives us amortized cost of almost O to the 2, which is O to the 1 because we dropped the coefficient term. Now to fill up that array of 8 elements, it would cost us 3 more. So 9 plus 3 is 12 to fill up 8 slots. So our total cost to fill up those 8 slots is 12. And we have a total of 8 elements that we can fill up. So that's 12 over 8, which is a big O of 1 to 1.5, which again we drop the coefficient, which becomes O to the 1. Basically we would do that several times across this whole thing and show that basically as we go out to infinity, our cost would basically, in the best case scenario, go to O to the second, and in the worst case, not O to the second, big O of 2, and the worst case of big O of 3, doing the initial capacity of 4. So as you drive that cost out, you'll see that worst case scenario, we're always at O to the 3, and best case scenario, we're always at O to the big O of 2, which, again, dropping the coefficients, averages out to big O of 1. We can show that with some initial capacity, showing how the cost is a little bit better with a bigger initial capacity. However, that kind of is not really the point. The point is just getting the amortized cost of this reallocation to be averaged out to a O to the 1 cost. Now, if we're also deleting elements here, obviously adding new elements into that list would actually drive the cost even lower than our two worst cases of big O of 2 and big O of 3 to something less than that, because the work to add those elements kind of gets more and more built into the equation. So looking at the worst case scenario, if we just kept adding and never went through or removed anything, our big O is big O of 3. So that's the worst case scenario. So that's all I'm looking for there, is a few pictures of the different arrays showing the amount to work and the cost of that. So showing, I believe, the initial array of like 4, and showing that expanded out to 8, and showing that expanded out to 16, and explaining the cost at each of those 3 array sizes and how that goes, and then making the jump of drawing that out to infinity, and kind of showing how that reaches a plateau of big O of 3 and big O of 2 would be good. So that's all section 4 is, and kind of drawing that and explaining that with a few words and everything. So there's section 3 and 4. Next I'll be covering section 5 and 6. Thank you, and I'll look forward to posting the next video shortly.